Okay, so generally, what is a sampling distribution? So this is where we started at the very beginning today. The second one that we did was the actual sampling distribution. The first one that we did was an estimation. So generally, what is a sampling distribution? It is a graph. It's a graph of dots. What do those dots represent? And it can be any. We use p hat today. It can be a graph of x bars. It can be a graph of s's. So it's a graph of dots that represent statistics from, this is the biggest part. And this is the part that I will definitely ask you a question about. Oh, yeah, I don't need your Chromebooks out. Put them up. And just like I said, guarantee you I will ask you about this. If I told you that this group simulated and they flipped coins and they wrote down all their data when they flipped coins, I would ask something like, let's say they did sets of 20 coin flips at a time and recorded the proportion of tails. And I would ask you, is this the sampling distribution for this scenario? And your answer would be what? No, it is a simulation, an estimation, because they did not use all possible samples of flipping a coin 20 times that there are. If I wrote out every single possible way that I could flip a 20 coins, like the first one would be all 20 tails, and then it could be 19 tails in a row but one heads, or 18 tails in a row, one head, then two tails. Like, so I would have to write out this huge thing that would be really long. It would actually be $1,048,576 different possible outcomes, which obviously you would not ever want to do. So the answer is no, and that is why. Questions on that? Because that is the big thing that I spent time on because of that. All right, so if I ever ask you to interpret, this is what I want you to write. A sampling distribution for a sample proportion. So we just had a graph of dots. We're just writing that a little bit better. Is the distribution of all values of, in this case, I would put proportion there, but I could exchange that out with something else. Proportion of whatever our trials are that were successful. From all possible samples of N trials. So if we did this with the example we did in class at the beginning, this would be a distribution of all values of what? Each of our dots represented a what? Each one of our dots represented a what? Proportion of numbers selected, what would be successful? That were yellow from all possible samples of, how many did we pick? 5 numbers selected. our trials thing is kind of funny there because it wasn't really a scenario. If this were flipping a coin 20 times and counting the proportion of tails, this would be a distribution of values of proportion of 20 coin flips landing on tails from all possible samples of 20 coin flips. So you're just plugging in your context stuff there. I would expect to see that as well. This one, a true sampling distribution of a particular statistic is what's above, what's explained above. So I would put just like an arrow up here. Almost never actually used, though. Back to that thing again of, is this a sampling distribution? No, this is an approximation of, because we did not use all possible samples. So then right below that, often a true sampling distribution of a particular statistic is not created, but instead we use a fixed number of trials, like our 21, to create, and this is what we did where we started, an approximation of the sampling distribution. So each dot on a sampling distribution represents a what? So like on ours, each dot represented a what? A what of a sample. So does it have to be proportion? Does it always have to be from a sample? So a specific statistic, which we did proportion today, for a specific sample. Each dot represents a statistic of a sample. When you did your own example, where we started with, and you found the mean of your own sample, was anybody's below 0.56? What'd you have? So go back to where we started with the 0.5524. Yours was below? 5429. What was yours? 0.5524. 5524. So 552. So we're about 0.02 away from the mean, right? To the left. All right. Was anybody's above 0.59? What'd you get? 6.095. I
just got 6.
6. 59105. 5905. 6095. 6381. 6. 0.6095. So those were maybe a little bit above. What did I say? Above 0.03. Is that right? I'm saying that right? How many people's were between 0.56 and 0.59? Raise your hand if yours is between 0.56 and 0.59. Should have a lot more than 2 hands there. I gave you 3 categories. Y'all should fit in one of them. So if I think about the way that is distributed, the average of my graphs, does that really vary much? No. So those average of my new graphs has very little variability, even though we only did 21 samples. So if we did a whole lot more than 21 samples, what do you think would happen to all of our numbers? So like if we put all of our classes' numbers together, what do you think would happen? You think the number would get bigger? The number would start to what? Get closer to what we thought it would be. So does that mean that it is biased? Is it biased if it's the same? No, it is unbiased. So a statistic used to estimate a parameter, which is what we were doing, is unbiased if the mean of its sampling distribution is equal to the mean of the population. That's what we're aiming for. We want that. If we did enough samples, we would get that. The sample proportion from a random sample of any size is an unbiased estimator. It's just giving you the different associations there. Larger samples, just underline this with me, larger samples are more likely to produce an estimate close to the true value of the parameter. That makes a whole lot more sense. If I wanted to know GPAs of the whole school and I interviewed 3 people, I don't know how close I would get. But if I interviewed like 300 people, I'd probably be getting a lot closer. So the more I sample, obviously the closer I'm going to get. Because I'm going to have much less variability if I have a big group, which we tie in later. So larger samples are also more precise. So just like what we talked about with the sample of your graph, they only varied down to like 0.55 and 0.6 something. That is not really that much because we now have the average of your averages. Those are getting really precise. The variability of a statistic, it's going to be different. It's not going to be perfect every time. Yours isn't going to be exactly the way that somebody's is beside of you. The variability of a statistic is described by the spread of its sampling distribution. Larger samples give smaller spread. Same thing we just said. So this paragraph's pretty obvious. We can think of the true value of the population parameter as like the bullseye on a target, and the sample statistic is arrows that we hit trying to aim for that target. So bias and variability describe what happens as we take many shots. Which one would mean that our aim is off and we consistently keep missing in a certain direction? Bias. So if I told you I was an 80% free throw shooter and you go out there and you get me to shoot a bunch of free throws and I start shooting closer to an average of like 60, there's bias there. My aim was constantly off. Maybe there's another issue. What means that our shots are widely scattered? Variability. What do you think ideally that we want? What kind of bias? Do we want a big bias? Is there going to be absolutely no bias? No, not unless we actually do the sampling distribution. Do we want variability? Do we want a lot of variability? No, we want low variability. So ideally, we're looking for low bias, low variability. We can do things like change our sample size to make that better. One big thing is if you increase your sample size, a lot of things are going to clean up. But there are reasons why maybe you can't. Cost options, resource options. This last part, I'm going to go through pretty quick. What is the difference? So this is the same graph, the same data on the same scale. So it goes from 0.22 to 0.52 on both of them. What is definitely different about the second one? What is definitely different about this one than this one? There's a lot less spread. The only thing that changed was we took all of them are 1,000 samples because this one goes 200, this one goes to 600. This was when we were dealing with each sample was 100. Here we were dealing with each sample is 1,000. So increasing our sample size changed the variability that much. It's not that we did more samples, it's that the size of our sample was bigger. So that fill in the blank, as long as population is much larger than your sample, that's the part that I haven't talked about yet. Don't worry about that part yet. But the spread of your sampling distribution depends more on your sample size than your population size, as long as it meets this criteria that we haven't talked about yet. We're just going to draw dots. You should talk about bias and variability in all four of those. So you're going to have something with variability, you're going to have something with bias, and each of those options are either high or low. So let's go through with bias first. Which ones have low bias? Which means these two have high bias. Which ones have low variability? Which means the other two have high variability. And which one is our ideal? A.